Hi everyone. Today in our lecture video we are going to study a topic related to Fourier series called half range series. Half range series are usually of the interval 0, L. So before going to half range series, let me recap Fourier series. So Fourier series is defined for the interval 0, 2L, and the function f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos n pi x by L plus summation n is equal to 1 to infinity b n sin n pi x by L, where it is a combination of both cosine function, sine function along with the constant. But the topic which we have chosen today is half range series, where your series either will be a cosine function or the series will be a sine function. That is half range. Either you can have cosine series or you can have half range sine series. So we have already studied the concept called even and odd function. You can have my previous video link, where cosine stands for even function and sine represents the odd function. Here you don't have to check whether the interval or whether the given function is odd or whether it's an even by replacing x by minus x or x by 2l minus x. We don't have to do it. Why? Because it is already mentioned the given series is a cosine series. That means it is already an even function. And the given series or a given function is a sine function, which is already an odd function. So we don't have to apply any condition whenever it is in half range series, because whatever they have given is itself an even and odd condition. Cosine means even function, sine means odd function. So whenever we have even function, we have to evaluate a naught an, bn term will be 0. And whenever we have an odd function, a naught will be 0, an will be 0, you have to evaluate bn. The formula remains the same as we have studied in even and odd function, but here the interval is 0 to L. So let's have a formula here for finding the value of a naught and an. For both I am just writing a naught is given by 2 by L integral, since it's in half range, 0 to L is the limit, f of x into dx, an again 2 by L integral 0 to L, whatever the length they have given, the complete length 0 to L we are supposed to take, f of x into cos n pi x by L into dx. Similarly, when you have a function that is half range sine series, bn is equal to 2 by L integral 0 to L f of x sine n pi x by L into dx. So this is all about the introduction of half range series. Half range series, we have cosine series and sine series. Formula remains the same as we have already studied with even and odd function. One benefit here is you don't have to check whether the function is even or odd, because it is already given. It's a half range cosine and half range sine, and the interval is half of the Fourier series, that is 0 to L. Now to understand the concept of half range, so let us consider an example. express a function f of x is equal to x has half range sine series in the interval 0 to L. So you need to check back the function. So always an half range series will be expressed in the form 0 comma L. So instead of L, you can see that it is given as 2. So first identify L, okay, for half range series. The interval will be of the form 0 to L. It is given 0 comma 2. On comparing both, L is equal to 2, which can be substituted in the formulas, right? Now since it is a sine series, you don't have to check whether the function is odd or function is even. It is sine series. So it is mandatory, it will be an odd function. So since it is a sine series, so I can just go with, since it's a sine series, directly take a naught 0, an 0. You just have to find bn. So that is 2 by L integral 0 to L f of x sine n pi x by L into dx. Since we know the L value, we can substitute wherever it is required, and the function f of x is given as x. So bn is equal to 2 by L is 2, so 2 by 2 get cancels. 0 to 2, x is the function, sine n pi x by 2 into dx. Carefully we need to apply the integration by parts, right? So on careful and integration by parts, you'll be able to understand what is the next procedure, right? So applying integration by parts, so bn is equal to first function. Always take first function as variable, okay, which terminates soon after some differentiation. So first function, integration of sine function, it becomes minus cos n pi x by 2 whole divided by n pi by 2 is the constant, so it is n pi by 2. First term, integration of the second term. So whenever we are integrating, the minus sign, keep it inside, because this term again goes for the integration. So first term, integration of second term, minus differentiation of first term. What is the x differentiation? Is 1. Twice I have to integrate sine function. One integration is already done here. This function itself you integrated once again. So I have minus 1 by n pi by 2, which is constant. I'll keep it out. I'm just integrating the cos term, which is sine n pi x by 2. Again n pi by 2. Now continue. Alternate plus minus sign. First differentiation of x is 1. Second differentiation will become 0. So the next term will not exist. Now carefully simplify, and the entire limits are ranging from 0 to 2. So bn is equal to what we have. I can take minus, so it is minus x. This can go to the numerator, so it is 2 by n pi cos n pi x by 2. Minus of minus become plus. These two are two terms, so it becomes 4. So it is 2 square 4 by n square pi square sine n pi x by 2 for the limit 0 to 2. Carefully apply the limit. Since we have integrated for x, limit will be applied for x. So bn is equal to, x is 2, so it is minus 2 into 2, 4 by n pi cos, 2 and 2 cancels out, so it is cos n pi plus 4 by n square pi square sine x is 2, so 2 cancels out, so we are left out with n pi. This is for the upper limit, okay, minus the lower limit. Wherever x is there, substitute is 0. So here x into this term, so it is 0 plus 4 by n square pi square. When x is 0, n pi by 2 into 0 is 0, so it is sine 0. Okay, so here we need to use condition sine 0 0, cos n pi is minus 1 power n, sin n pi is 0. Kindly substitute these values in the above equations. What we get when we substitute? Bn is equal to, this term becomes 0 and this also becomes 0. So we are left out with minus 4 by n pi cos n pi. So this is a simplified form. And what is cos n pi? Minus 4 by n pi minus 1 power n. Okay. So this is a value of Bn, right? Now you can apply this in the Fourier series. So Fourier series for half range sine is having only Bn term, that is n is equal to 1 to infinity Bn sine n pi x by L. L is 2, so you can substitute it there. So we get n is equal to 1, 2, 3 also we can substitute. So n is equal to 1 to infinity Bn sine n pi x by 2. Start expanding the summation. Start putting n is equal to 1, 2, 3. So you will get completely a sine series. And what is Bn? We have got Bn is equal to minus 4 by n pi minus 1 power n. You can substitute it. Keep n inside the summation. The other constant you can keep it out. So it is minus 4 minus 1 power n by pi, because n is depending on the summation. So summation n is equal to 1 to infinity 1 by n sine n pi x by 2. Expand the summation by substituting n is equal to 1, 2, 3. So minus 4 minus 1 power n by pi. Yeah. So n is 1, so it is 1 by 1 sine pi by 2x minus 1 by 2 sine 2 cancels out, so it is pi x. Put n is equal to 3. Okay, this is plus 1 by 3 sine 3 pi x by 2 plus 1 by 4 sine 4 pi by 2 is 2 pi x, and so on.